We were talking about heats of formation, and we looked at how we can write formation equations for different compounds. And then we look up the standard heats of formation in a table. So that standard heat of formation corresponds to the formation of the compound from its elements in their standard states, 1 mole of the compound. The opposite of that, the negative of that, would correspond to the opposite, which is 1 mole of the compound being decomposed into elements in their standard states. So what we can do is we can calculate the enthalpy of any reaction by, in our minds, taking the reactants apart into their elements in their standard states, and then putting them back together into the products. So taking them apart is negative heat of formation, putting them back together is positive heat of formation. We can write a reaction as the sum of formation reactions, or the sum of forward and reverse formation reactions for the reactants and products using Hess's law. But we don't actually have to write those equations out. So the heat of reaction is the sum of the heats of formation for those component reactions. So it's the sum of the products minus the sum of the reactants. So this capital sigma means sum of, and n represents the coefficients. So if you have a product where there's 2 moles of the product, then you have to multiply the delta HF by 2 because you're making 2 moles of it. If you're breaking down 3 moles of something, you multiply it by 3. So we're going to look at the complicated way and the not complicated way to do this. So here's an energy diagram representing the combustion of methane. So we're starting out here with methane, and it's reacting with oxygen, and it's producing carbon dioxide and 2 moles of water. So these are the formation equations for the compounds that are in the reactants and products. So we've got methane. This is the heat of formation equation for methane. Oxygen doesn't have one because that's in its standard state. And then we have CO2 and we have H2O. CO2 and H2O. So using Hess's law, we can take these equations. Let's see, what am I doing? And we can color code them like we did before. So there's there's methane, and there's CO2. And we'll use blue for water. So we could take these reactions here and combine them to get this overall reaction. So I'm going to do that kind of quickly. We want methane as a reactant. So I'm going to choose this one and reverse it so that methane is a reactant. So CH4 gas going to carbon. I'll just put GR for graphite, plus 2H2. And then the delta H for that, because I reversed the direction, I'm going to change the sign, right? So that's going to be plus 74.6. So I've got my methane. And then CO2 is going to be this one. I need CO2 to be a product. Here CO2 is a product, and so I'm going to put that one in there as it is. So here I've got carbon as a solid in the graphite form plus O2 gas making CO2 gas. I didn't do anything to the equation, so I'm going to just copy down delta H as it is. And then I need water as a product, and so that's this guy over here. So H2 plus 1/2 O2 making H2O. Does this have the correct coefficient on it to match up with the equation we're trying to make? No. This is 1, and I need it to be 2, so I'm going to multiply everything there by 2. So I'm going to get 2 hydrogens and 2 water molecules, and when I multiply 1/2 by 2, I get 1, right? So then I'm going to have 2 times the delta H. Not enough space here. And then if I'm adding these things together, I see I have carbon as a product and a reactant, so those cancel out. I have 2 hydrogens as a product and a reactant, so those go away. And I end up with methane, 2 moles of oxygen, carbon dioxide, and 2 moles of water. Does that look at least slightly familiar to something we did on Tuesday? Kind of. So to calculate delta H for that, then we're going to add these things together. So we're going to have 74.6 plus negative 393.5 plus 2 times negative 241.8. Oops. So delta H for the reaction is negative 802.5 kilojoules. So that matches up with this one over here. I guess I should put that as a standard. That's kind of messy and tedious and confusing, huh? So instead of actually doing all of that, we're going to just sort of take a shortcut. Because what this is the opposite of forming a mole of methane, right? It's taking apart a mole of methane. So that would be subtracting to get so we're subtracting negative 74.6. Over here, we are forming 1 mole of CO2 and 2 moles of water, and so we're going to have this and 2 times that. And so what we can do, instead of adding up all these equations, we can say that delta H for the reaction is equal to the heats of formation for the products. So we've got CO2, so we're going to have the heat of formation for CO2, and 2 times the heat of formation for H2O. So we're forming this, and we're forming 2 of those, and then we're going to subtract the heat of formation of methane. So products minus reactants, like final minus initial. So we're forming these, and so those are positive, And then we're decomposing these guys, and those are negative. I left O2 out because the heat of formation of oxygen is 0, because it's an element in its standard state. So then what we end up with here is the heat of formation of CO2, which was negative 393.5. I'm leaving the units out because I don't have enough space. Plus,
Why is it CH3?
because I wrote the wrong number. Thank you. I don't know. Yeah, this is supposed to be CH4. That's a very good catch. Thank you. Yeah, so then the 2 times the heat of formation of the water, 241.8. Minus the heat of formation of the methane, because we're taking it apart. So that's negative 74.6. So these numbers here end up being the same as what we came up with over here. We have positive 74.6 because we're subtracting negative 74.6. We've got 393.5, and we got 2 times negative 241.8, and so we come up with negative 802.5 kilojoules. Any questions? Let's do an example. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. It's a very spectacular reaction. Use standard enthalpies of formation to find delta H for the thermite reaction. So what we're going to do here, we're not going to add up equations because we now know we don't really have to do that. The heat of reaction, standard heat of reaction for this, is going to be the heats of reaction of the products, the heats of formation. Well, I guess I should write it out like this. The heat of formation of Al2O3 plus 2 times the heat of formation of iron minus the heats of formation of the reactants, 2 times the heat of formation of aluminum plus the heat of formation of Fe2O3. You have a question?
Do you always subtract the reactants?
Yes. You always subtract the reactants. We're subtracting the reactants because instead of forming this, we're unforming it. So instead of adding, we're subtracting. So do you see the overall picture of what I'm doing here? I'm looking for the heats of formation for everything I'm producing. There's a 2. I multiply iron by 2 because I'm making 2 moles of it, right? And then I'm going to subtract all the things that I'm decomposing. And again, there's a 2 in front of aluminum because there's 2 of those. But some of these have heats of formation of 0. Which ones? Iron and aluminum. This is an element in its standard state. And I'm not going to try to trick you with, oh, it looked like it was in its standard state, but it really wasn't. You know, aluminum, you look on the periodic table, aluminum's a metal, its symbol is black. Here it's a solid, black means solid. Yeah, it's just that straightforward. The only kind of confusing ones are things like carbon, right? Graphite or diamond, and I'm not going to try to confuse you with that one. Here's another one, aluminum. We've got aluminum and we've got iron. Iron is just an element. It's not a compound. It's an element. It's a solid on the periodic table. So those guys are 0. So this one is 0, and that one is also 0. So then we don't need to consider them. So what we need to do is we need to look up the heat of formation for Fe2O3 and the heat of formation for Al2O3. I thought maybe I had hidden those in there, but I did not. So we'll go over here. Fe2O3, solid. So the heat of formation is negative 824.2. Negative 824.2. And the other one I need is the aluminum oxide, right? Al2O3. Make sure that you get the right compound. The heat of formation, negative 1675.7. Negative 1675.7. So I just looked those up in a table, okay? So the heat of reaction for this then is going to be the heat of formation of aluminum oxide, negative 1675.7, plus 0, minus this quantity, right? Minus all of these things. So minus the 0 and minus that. And then don't overthink this, just let your calculator deal with those negative signs. And it works better when I type the numbers in correctly. Negative 851.5 kilojoules. Any questions? So this is a quick way to estimate the heat of reaction for anything. You can find the heats of formation of all the compounds that you might want. And so you can add and subtract those to get an estimate. This is not going to be exact, and this is only at standard state, which would be standard temperature, the standard temperature of interest, which would be probably room temperature. So if you were doing something at a different temperature, you'd need to make some allowances for that. Lost in my slides there. Okay, here's another one. So back to those chemical hand warmers. They produce heat when they're removed from their packaging. Here we have the chemical reaction. It says calculate the heat of reaction for this reaction and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Well, before I start writing over here, we're going to need the heat of formation of the Fe2O3, which, ideally I would remember since we just did that one, but I don't. 824.2. So if we have a hand warmer that has 15 grams of iron powder in it, how much heat is it going to give off? Well, if we knew delta H for the reaction that's occurring, we could use that to calculate, but they didn't give us delta H. They're going to make us calculate it, right? So to calculate delta H for this reaction, we're going to take the heats of formation of the products and subtract the heats of formation of the reactants. What are the heats of formation of those reactants? 0. So here then, the heat of reaction is going to equal the heat of formation of that product minus the heats of formation of the reactants, which is 4 times 0 and 3 times 0. Yes?
The heat of the formations are negative because they're giving off heat, right?
Yes. Most heats of formation are negative, but there are some that are positive. Oh, what did I forget? Coefficients. I put coefficients here. I forgot the 2. Kind of important. 2 times that. So that's going to be 2 times negative 824.2. Oops. Negative 1648.4. So for that reaction, delta H is negative 1648.4 kilojoules for the reaction as written. Now they're saying you've got 15 grams of iron powder, and how much heat is produced? We have a chemical reaction. We have an amount of substance here, maybe orange. So we've got 15 grams of that, and we want to know how much heat is given off. So think about grams to moles to moles to grams. Are we starting with a mass? Yes, we are. So we're going to go mass of that to moles of that, but are we ending up with grams? No, we're ending up with kilojoules. And when we have energy involved, we get to skip the second mole. So we don't need these guys. We can go straight to kilojoules, because this relates directly to any of these. So we don't have to go moles of this to moles of that and then grams. So then we've got 15 grams of iron, and we'll have to convert that to moles. So the grams will cancel out. And then we're going to go to kilojoules divided by moles of iron. So that first conversion factor is the molar mass of iron. And this last one is our delta H for the reaction. Negative 1648.4 kilojoules for how many moles of iron? 4. Moles of iron cancel out. So 15 divided by 55.85 times negative 1648.4, and then I often forget to divide by that 4. And so negative 110.7 kilojoules. would we say that negative 110.7 kilojoules are produced? Do I say that I paid negative $100 for shoes? No, I paid $100. The negative is implied by saying paid, right? So here produced stands in for the negative. So if this is a mastering chemistry question, they're going to want you to answer this as a positive number, right? So 110.7 kilojoules of heat is produced. And that negative or not negative there, that's another thing. I'm not going to try to trick you with that, like on an exam. But it can be very confusing when you're doing the homework and you're like, yeah, but the calculation gave me a negative number and they're saying it's positive. What's up with that? There's a reason for it. Any questions? You rounded to 3 sig figs. That's right, it should have been 3 sig figs.